Okay, this is the last part for chapter 7. We're going to talk about designing now with compression reinforcement. Now, we have talked about compression reinforcement before, right? And we know, as explained, the beams in general have compression bars all the time, right? But we don't design for those. Those are for the cage to support your stirrups. But when you properly design for compression reinforcement, you do increase your capacity. Now, usually, you will try to use compression reinforcement when the cases where you have small sections, the depth is small because of clearance requirements. So in those cases, you will use that. The problem with that, because you're using a smaller section, right? There is always the possibility for issues with deflections. There is also the problem with overloading in shear. And so those things need to be considered when dealing with compression reinforcement. So the general procedure that we're going to follow, let's go some of these formulas that you've seen already. The first thing we need to know is, in general, right? Is it the compression reinforcement yielding? Okay. And we have used these inequalities. We check that. Then, of course, we check for if it doesn't yield. Then we have to find the neutral axis, because with the neutral axis we can find epsilon prime s, that is the strain value on the compression side, and then by multiplying times the modulus of elasticity, we get the actual stress of the compression bars. These values should always be below Fy, right? And then we can use the formula here that we developed in chapter 5 to find the A value. And finally, of course, we will check our values. So that's kind of the what we learned, some of the formulas that we have used. And now we're going to get the actual design part. Okay? This is when, again, like we did in the regular beams, this is the case where you know B and you know your height, basically. Okay? So there are two methods to solve this. Okay. One method is simply to design things, right, as tension. Okay, so you say, okay, I'm going to treat it as a tension member, right? And so what is going to happen in that case is that you epsilon T, right, your strain on the tension side is not going to satisfy ductility. Yeah? So what you do is you will use the compression reinforcement. Remember, the compression reinforcement, what it does is increases ductility. So you will use compression reinforcement to increase the ductility, right? But you already got your moment capacity based on your tension bars. Okay? So what's the idea then? You start by taking your moment, right? And so you take your moment from the applied loads. You assume a F factor of 0.9, you divide, you get your M sub n. You find the area of steel that you need for this moment. Yeah? If this area will be usually, if you need compression reinforcement, the area will be a lot higher than the AS maximum. So you're not satisfying ductility, right? And so you need to improve that. Now, if the area that you find by doing this is not higher than AS maximum, it means that you don't need compression reinforcement, okay? So you're good. So you just did regular tension beam, all right? Now, because the typical case is going to be that AS maximum is not going to be satisfied, right? You need to improve the ductility, and you're going to add is arbitrarily you are going to add compression reinforcement. Now, to get a good ductility, the amount of compression reinforcement that you want to add should be half the amount of the tension steel that you found in step 2. Okay? And then you go again, and now you check your epsilon T and phi sub n. But how you're going to check this? You're going to go back here, right, to these equations, and you're going to check it. Okay? So let's recap on that method 1, which is the easiest. Okay, that's the easiest method to design these beams. So you design as regular tension, you check, and your AS maximum is not satisfied. Because AS maximum is not satisfied, right, the option when using compression reinforcement is to add compression reinforcement. And you're going to add this arbitrarily. Mm-hmm. If you add about half of your tension reinforcement, then you're going to increase your ductility significantly, and most likely the beam is going to pass. But you have to check it back again using all these formulas, going all this way, and check it. Okay? So that's method 1. Okay? Method 2 is more of the classical approach, in which you will find, right, the maximum amount that you can carry with the tension bars, with the AS maximum, basically, right? And so that will give you the moment that you can carry with tension only. Your apply moment is going to be higher than that. So you find the difference. The difference is then what you need to carry by compression bars. Mm-hmm. So that's the other method, right? So you do that. Okay? And so you will have again to select an epsilon T, and this epsilon T is going to be, in most cases, that value is going to be your tension control value, right? Because that will be the smallest section you can use. In some cases, people like to use 0.0075 in here, but you don't want to go below that height, right? But in most cases, this is going to be tension control. So I'll give you the maximum that you can carry with your tension bars. So you follow your procedure, you find your area. This area is your tension area that you can use to carry this moment, right? That gives you a moment. Yeah. And so you find what this moment is. Again, I mean, if so happens that this value, right, is greater than your apply moment divided by your phi factor, then you don't need compression reinforcement. There is no difference, right? The idea of the compression reinforcement is that when you design for the tension bars, you found a capacity, but that capacity is not enough to carry your moment. So you need to have a difference. And so this is really the case. So the case is really this one. Your M sub n that you find with the tension only is less than what you need, and therefore there is a difference. So then you find the difference. The difference is what you carry with your compression reinforcement. Okay. And so your F prime S, you need to find it again. And so that means you need the C value, you need an epsilon prime S. And again, I mean, you cannot exceed Fy, right? Once you find your epsilon prime, your epsilon prime S, you can find the A prime S, the area that you need in compression, by simply making the area of the tension bars, right? The second area. This is a second area. So you found here an area, but this is a second area that you need to carry the extra moment, right? That second area has to be equal to your force due to the compression. Okay. And so that solves now for your new area in compression. Okay. Now, if so happens that the compression still also yields, then these two are equal, and then the AS2 is the same as your compression steel. Okay? So those are the 3 steps. So we're going to see that. Let's look at what we have here. There are some additional requirements. Now you're looking at bars in compression, right? And we discussed it already. You have bars in compression. The potential for buckling is there, and therefore the code specify now the size of your stirrups, right? So before, I mean, you can say, oh, I can use whatever I want, whatever I need according to my shear. But now there are minimum values in terms of the size of the stirrups that you can use. Okay. In section 97641 in your code, under beams, okay. So beams, right? So 97. Let me go first there, and then I'll make it bigger. All right, let's see. I may have the wrong code here. Let's see, 97. Oh, that was in the wrong place. So, okay. I think this is where we have it. Let me make it a little bigger. So 9761, lateral support of compression reinforcement. Okay, this is what you're looking at. All right. So where you have longitudinal compression reinforcement, you must provide transverse reinforcement. Okay, and that lateral support is specified here, all the way through here. So first, the size. If you are using number 10 or smaller bars, you should use at least a number 3 stirrup. Okay. You go to number 11, you must use now a number 4. Before you didn't need that. Before you could have used number 3s. Okay. But now, because you're putting compression bars, number 11 compression bars, you have to use a number 4. Not only that, these stirrups, ties, because they had to be ties. They had to be completely closed. Okay, they cannot be open. They had to be closed. You also have the requirement of the spacing. The spacing of these ties, let's call them ties because they're closed. Okay, they had to have a spacing of 16 times the diameter of the longitudinal reinforcement. That is your compression bar. Okay. So your compression bar is a number 8, which has a diameter of 1 inch. Then these ties have to be spaced either at 16 inches. That's one choice. If you use a number 3 stirrup, right? That will be diameter of 3/8, right? And so that would be 18 inches spacing. So far that one governs, you're using 1 inch. Or the least dimension of your beam. So you have your width and your height. In most cases, the width is the one that controls that, right? So that will be, so you look at these 3 numbers and you pick the smallest, and that's how you place your ties. Okay? So the other thing here is this one. You need to place it such that every corner, okay, and alternate compression bar shall be enclosed by the corner of a transverse reinforcement with an included angle of no more than 135 degrees. and no bar shall be further than 6 inches clear on each side along the transverse reinforcement from such an enclosed bar. Let's see, they have a drawing here. Okay. I don't see a drawing there. So let me see if I can show you something. Maybe it was in columns where they have it, but there is a drawing in the ACI. Okay, so let me do then this. Go back to the chapter 7 that we were working on. Right, and let me see if I can do this. Show you what they mean. Now here is the part that I usually fail to do, right? Okay, so you're going to have your beam, and you're going to have, let's say, 3 bars in compression. So you're going to have then an element here, your stirrup, right? But it's closed, and it has to have these elements here, right? Completely closed. So, and the angle here, that angle, that's what they're talking about, the 135 degrees. Oops. Right. So now we have then that angle is 135 degrees. Okay. Okay, so that's the 135. Then this says also that you have to cover the corners, and you could skip 1 bar. That's all you can skip. Okay, as long as the clear distance. Oops, I don't know. As long as the clear distance is no more than 6 inches. Okay, so you can only have a clear distance of 6 inches. Six inches. Okay. Now let's do something, another beam. A little wider. Right? So I have that. Right? I can only skip 1. Remember, that's all you can skip as long as you have 6 inches. Right? So what that means is that I have to put something here that comes like that, right? And it takes care of that one. Right? And I will have to come in here and do something like this, right? And I can do it there, I can do it here. Mm-hmm. So I have to do that. So I can skip this as long as it's less than 6 inches. If it's more than 6 inches, I have to provide stirrups also here. Okay, so I have to cover that too. So they will need something there. So that means you will have to provide extra here if you have more than 6 inches. You cannot leave it by itself if this distance, the clear distance, is more than 6. Okay? And there are different ways to arrange this, right? But you have to now cover everyone. If this clear spacing is more than 6 inches, so every bar has to have these ties. Okay? If it's less than 6 inches, you can skip 1. Okay? That's basically what they mean by that. So let me do one thing here. because I had two of these versions and I don't want to have two. So let me just keep that one. So this is the one we're using. Okay, so design examples. Let's start with that. So now we're going to do our design examples. So we have here a beam 12 by 18 to carry a negative moment of 280. We're going to use number 3 stirrups, so that means our compression bars cannot exceed, or you're going to start with that. That's an assumption, right? But then as you find your bars, right, you find bars that are, say, 11, that means you had to use number 4. You're going to use the number 3. But we try number 3 first because, I mean, that's cheaper, right? All right, so there is the strength there. We're going to sketch our solution. And so we come in here, we find our tension, steel, like we normally do, right? So assume the 0.9D, get a value, right? Then you can recalculate this, get a better answer. So I got my 509, check my A, check my C. I notice that, whoa, I mean, this does not satisfy the limit for grade 60, right? And so ductility definitely didn't work, okay? So what we can do is go here and say, okay, we're going to use method 1. Method 1, it says, take advantage that the UR compression reinforcement, you increase ductility. Okay, but how much should I do, right? Okay, so we're going to take half of what we needed. That's the 509. Half of that, 255. So well, we will look at the tables. Probably these 3 number 9s are good. Okay, so we use 3 more. So we're using 3 number 9s here on the compression side. Remember, the compression side is at the bottom. Why? Because this is a negative moment, right? So negative moment, tension at the top, compression at the bottom. Okay. So I'm going to use that for compression. And for my tension reinforcement, I'm going to use 3 number 11s. Okay. 3 number 11s. Now this is less than the value that we got there, right? But really, I mean, that is what we can use in one layer. Otherwise, if we go to double layers, then we have to change the D, we have to change all those calculations. So we're trying to see if it fits, it will work. We don't know, okay? So remember, everything has to be checked. So you're just taking a chance here that, okay, I'm going to go a little lower, but I did add more compression reinforcement here. So maybe we get something. So now this problem becomes a problem like this, right? And in this problem now you have everything defined. So once you have everything defined, this is the case that we learned in chapter 5, how to find your M sub n and your phi M sub n. So that's what we're going to do. So now that everything is defined, I'm going to find my A prime S, my AS, my D's, my D primes, right? Go into the checking to see if it's yielding or not, right? So we do the values, doesn't yield, so that means I have to find my neutral axis. With the neutral axis, I find my epsilon prime S, take that value, multiply by the modulus, get my stress in the compression bars is less than Fy, so that's good. Find my A value, multiply by beta 1, so we get that is greater than D prime. Remember, it has to be greater than D prime, otherwise the bar is not in compression, right? And then we find our N sub n, check ductility, and notice this, okay, right there, the increase in ductility. Now we're good in ductility, see? Very, very good, right? Compared to the one value for grade 60, right? So that's the advantage of doing that. So completely arbitrary. So we satisfy that. We find the moment. The moment didn't quite work. I mean, it's close, but not quite, right? We needed 280, it's 279. I would say probably right. Okay. But some lawyers may not. So let's see what happens if we don't use the 3 number 11s and we actually do 6 number 9s. Okay. So we had to do it in double layer now. It's 6 number 9. Now this satisfies the area of steel that we needed. Plenty, right? We keep our A prime S the same. So we go here again, find A prime S, AS, find my D sub T, my D prime, check if the steel yields. It doesn't yield. I need to find again my neutral axis, find my epsilon prime S. With that value, I get my F prime S, find my A, right? Put it in the formula for the moment, find my values. I notice that I got 360. I need to check my ductility. My ductility went down because of the amount of steel I put, right? So it didn't quite work because we put 6 number 9s, right? And we only needed what it was 5 or 9, all right? So what are the options? So this does not work. So what are my options? Okay. So I got capacity, I got nominal capacity, but my design strength did not work simply because I barely went below the limit, right? So it was a little bit. So 2 options. I can change the amount of steel I put on the tension side because I went to 6 number 9s, right? So let's look at that. That's a possibility, right? So I went higher because I'm doing double layer. Remember, you go double layer, you lose D. And if you lose D, you need more area. So when I pick up more than what I needed. But maybe I can do a little better. 7. Oh. No, that's too much. We did 6 already. So we want to do like 550. So here. 7 number 8s. Oh, but if we're doing double layer, that would not work. Okay? So 7 bars will not work on double layer because you are required to put your bars on top of each other. And so that means, right? So if I have 1, 2, 3, 4, and then I'm going to put 3 more to complete 7, right? 1, 2, and 3, because they had to be on top of each other. So this is not symmetric, so not good. Okay? You cannot use 7 in double A, right? So definitely not. So let's keep looking. So we don't want to go to 6. But we want to go to 5. So maybe we combine. Let's combine 3 and 2, for example. Right? So you can do 3 number 10s, or 3 number 9s with 2 number 10s. You can also do 2 number 9s with 3 number 10s. That's a little less now than, wait a minute, that's 4, no. Yeah, that's 581. So it's less than 6. So you're putting less area of steel. So that will reduce the problem that you have with your ductility, right? So you can reduce then the amount of steel by using a combination of bars. So that's a possibility. If I do that, I would say do 3 number 10s and 2 number 9s. So that way you put the 3 number 10s on the first layer and the 2 number 9s on the second layer. Okay? And so that reduces your area of steel. Another thing that you can do, right, is the same that we've been doing for the compression, right? If I need to improve my ductility, if I can add a little bit more of compression steel, that will improve my ductility. So I can change it to 3 number 10s. So that's one choice. So let's go back here, right? My choices are change this to 3 number 10s and then 2 number 9s, and leave this as 3 number 9s. And most likely that will work. Right? It has to be checked, but that's a possibility. The other option is leave this like it is, but change this one to 3 number 10s, because adding more compression reinforcement increases my ductility, right? So put here 3 number 10s. Mm-hmm. So that's the problem with working again with very small sections, right? And you probably saw that in your homework, trying to deal with that the smallest section. You move a little bit off, right, of what you need. The section goes, it doesn't satisfy your ductility, right? Very easy. So that's one of the problems. So that's why this is where you have to think about it. Okay? So how do I improve ductility? I can change my compression reinforcement, make higher the value of the compression reinforcement. That will increase my ductility. Since I am very, very, very close, right? All I need is a little bit more. So then I said from 3 number 9s to 3 number 10s. And that most likely will satisfy. Now you don't want to change this. Then the only way you can improve this is by reducing the amount of tension that you're putting. You're putting 6 and you don't need 6, right? You only need 5 or 9, but because of the double layer, you cannot go with 5 or 9, because 5 or 9 is based on single layer. Double layer requires more area of steel, so I will try 554 or 585 on that range. And so that will be then using in here, right, 3 number 10s and 2 number 9s, and that most likely will work. And you keep this the same. Okay? So those are two options. So notice again, there is not a unique solution. Okay? There are different options on how you can solve that. Okay? All right. Now you would have done method 2 now, right? Okay. So now we use method 2. In method 2, again, you go with the smallest possible section, right? So you use the 005. Okay? So that gives you the maximum amount of steel that you can put in this cross section, right? So notice that I really didn't need a specific formula for A is maximum, because all I need to do is, in this formula, all I need to do is replace my tension control value, and that's A is maximum. So for the given section, this is my A is maximum. Okay? So I multiply that in my given section, 12, 15.5. So that gives me my area. Right? And then with that area, I find my A. With that, I go ahead and find my moment. So if I use the maximum amount of steel, tension only, this is all I can carry, right? But I need to carry 280. Okay? Now notice that this is an M sub n. So my 280 has to be changed to an M sub n. So I divide by 0.9, assuming that I'm going to develop my ductility. And so really I need to be at 311, and this is 219. Okay? So I find the difference. This difference needs to be carried by the compression steel. So now I make it that one equal to my compression steel equation. Okay? And I solve, and I get an area. This is the additional amount of tension steel that I need. Notice that here, I didn't find bars. All I did is, this is my area. Okay? Now I'm going to add this extra area. So I need 478. With that, now I can go to the tables. I didn't find the 478, but I found something close, but it's on the low side. So we'll see. Okay, 3 number 11s, 468. There. So I find now my C value, since I know my A. Find my epsilon prime S, because I need that to decide what the compression bars are going to do. So the value is pretty low, so I find my F prime S below the Fy, so that's good, right? And now I find my area of the compression bars by doing this other formula, right? Because the tension that I added has to equal the compression that I'm trying to develop. Okay? And so that gives me 172. So this is the area I need for the compression bars. Okay? So I go to the tables, I pick 2 number 9s, and there it is. So now I have an A prime S of 2, that's my compression bars. And I got an AS of 468, which are my tension bars, right? So I got 3 11s and 2 number 9s. So with that, I set up again to check, right? Check the area, see if it's yielding. Conclusion, not yielding. So I'm going to find my neutral axis, that gives me 536 as my neutral axis, right? Notice that it's not the same as here, right? Because here we're still guessing and things. When we put these bars, your neutral axis changes. So that's what you need to understand. That by doing this, you're changing your neutral axis. So now you need to find a new one. So that's why we did all this. So now this is the neutral axis with the compression reinforcement. You find your epsilon prime S, and so that's also changed. You get an F prime S. Find your A, find your N sub N, and then check your ductility. Ductility was a little above the 0.0054 for grade 16. So multiply this by 0.9, right? And we get 276. A little there, but not quite, right? What did it make it? Okay? So, like the case method 1, a solution with larger capacity, right, is obtained by having 6 number 9s and 3 number 9s as compression reinforcement. You know? Another possible solution is to do 8 number 7s on the tension side and 4 number 7s on the compression side. And I like this solution right here. Okay? I like that one a lot. Why? Yeah, exactly. All the bars are the same, right? There is less confusion in the field. I mean, there is less confusion. All the bars are the same. The only problem the guy is going to have is what goes on the top, what goes in the bottom. But at least the bars are going to be the same, right? So this is another, that's a very good solution. Okay? Now let's look at the solution in terms of areas. Okay? So 8 number sevens, 8 number sevens, notice that is here. It gives you 480. Okay? 480. Okay? So it's still there. I mean, kind of less, 480, right? Compared to what we originally needed. Let's see what we needed originally. So we're still below. So 478. Okay. So not bad, right? 478 and 480. So that one is good. So 8 number sevens, right? So 8 number sevens, good selection, right? And that will give you your solution for this case. Okay? And why will that one be a preferred solution? Simply because all the bars are the same, easy to deal with in construction. All right, let's try another example here. We have the loads, right? Top cover is 2 inches, bottom cover is 1.5. The material properties, number 4 is stirrups. And the bars that are shown here is just for reference. You're going to have bars, the number we don't know. Okay? All right, so we, again, find our factor load, right? Because it's simply supported, we find our moment. Take that moment, divide by 0.9, right? I put 0.005 here to find my maximum amount of steel. Find my D value, assume a value, of course, right? And with that, I get my area of steel. With that area of steel, I find my A. And with that, I get my moment. So this is the moment I can carry. Nominal. Okay, this is the nominal value. The actual moment that I need to carry is, in terms of nominal, here I change it to nominal, right, is 1,195. So we are short. Since we're short, we might wait the difference. So the difference needs to be carried by the new area of steel. We need to find D prime, 3 inches, that's good, still within the distance, right? And then we find the area is 137. This area now is added to the first area, right? And so the first area was A68, you add that, now you get 1005. So this time I pick higher value. 8 number 10s. Right? This is higher than that. So, but you have to use double layer. Okay. Because of the double layer, you will have a smaller D, right? And it is better to select a slightly higher area than required. So, I said, I think I'm going to go with 5 number 11s and 3 number 10s, or 8 number 11s. For simplicity, we're going to take the 8 number 11s. Mm-hmm. So it's more area simply because we have lost the D value, right, in double layer. All right. So with that, approximate my C, get my epsilon prime S here, value. So find my area of compression steel, right, by equating the tension force on the additional tension force with the compression force. And that gives me 2 number 8s, so that's 158, which is more than the 140, so that's good. And then we're going to check the capacity. So now we have 2 number 8s on the compression side and 8 number 11s on the tension side, right? Find our D based on the number 11s, right? And then find our D sub T. Go and check yielding of the compression reinforcement. Compression steel yields. Well, that makes it simple. So now all I have to do is use this formula for the A. I have to find the neutral axis. Right? Formula for A. And all this is given in your design aids, okay? So you don't forget. I mean, design aids, you have several things here. Okay? The formulas for compression reinforcement are here. If it yields, right? If it yields, you have it here. Okay? So there it is, right in here. So you have it. Okay? So all these formulas are there. Okay? So we use the formula, put it here in M sub n, find my M sub n, check ductility. Oh, ductility is not good. 33 compared to 0.05. Okay. So the fact that we put more area than required, right, has resulted in this problem. Remember, when you add more steel, what happens? You need more neutral axis. You need more neutral axis. You're moving towards the left of that curve on your phi factor, and that's what this one happens. Right? So how are we going to correct that? We need more ductility. How do we get ductility? We add more compression reinforcement. So instead of 2 number 8s, we're going to do 4 number 9s. Now I did try 4 number 8s, but it didn't work. So 4 number 9. So now I changed my compression steel to 4 number 9. So notice how I did, okay? I followed the procedure, I found my difference, I found all that, but at the end it didn't work. So all I had to do then to improve my ductility is add compression bars. Right? That's a good concept. So I do that now, checked. Compression steel yields, so it's good. So we use the same formula, check my capacity, check my ductility, and I barely made it, but hey, it's past the 0.05. So now it's good, phi factor, and I got enough strength to carry my load. So when you're doing compression steel and things, ductility does not satisfy, there is no need to panic. You just have to use your concept, right? If I add more compression steel, I will improve my ductility. If I reduce the tension steel because I may have exaggerated, then I can also improve my ductility. Okay? So keep those things in mind. Now, all the formulas that we have been using here, right, as I said, they are here in your design aids. These are the formulas for checking that we've seen already. But the ones that you're probably looking for is, what is this equilibrium that you're doing with tension forces and all that? Right here, this figure, okay? So when I said my additional tension has to be equal to my compression force, this is what I'm doing. So we're making these two equal, we get this formula, okay? And this is how you find your area of steel. So what we do is then, first, we find how much we can carry with the AS maximum. So this AS 1 is your AS maximum. So find the moment that you can carry with AS maximum, that's your N1. Excuse me. Then we subtract that from the actual M sub n. That gives you the difference. The difference needs to be carried by the compression steel and more tension steel, right? And these two have to be in equilibrium, so that gives you this formula. Notice here is the formula for epsilon prime s, and here is the formula for f prime s. Okay? So this one is the first step, and this is the second step. Okay? So let's go back, just recap, right? So you come in here. So this is first step. Okay, you're finding the first area. So that's N1, first step. Okay. So you have found this moment. Okay. Now we're going to find this one. So we do the difference. Okay. So we do the difference. That gives us what we need for number 2. But this moment, right? This moment has to be equal to the product of AS2FY times the arm between the two forces, which is D minus D prime. Okay? So this one times that gives you the second moment. All right? And then by equating your compression force, so your moment and all that, you solve for your area, your tension, your additional tension, sorry. This is your moment and your tension, right? So you find your value. And now you add to what you found before. So do not find areas when you are here, okay? You find areas after you find your second tension area. Now that you have your second tension area, right? You find your F prime S, and you use this equation to find your A prime S, right? And what equation is that? Is just simply this one right here. Okay? If it yields, this cancels, and both areas are the same. Okay? Okay, so I think this is the end. I don't think we're going to do any non-rectangular, so we're not going to do that. And so that will be the end then of this chapter.